Okay, good morning, everyone. It's a pleasure to be back. Today we'll have a second set of our lectures. And as I promised to you yesterday, there are going to be two lectures on two topics. One is about quantum communications, and second one about quantum sensing. Quantum communications with single-photon and entangled-photon state. Basically, the second, originally when quantum communications came about, it was mainly about quantum cryptography. That will be the subject of today's lecture. However, yesterday I mentioned to you that these days quantum communications is a broader area. What does it mean broader? It's broadened into the issue of distributing quantum states between different nodes of the network. And I will touch it a little bit only tomorrow, but in regards to some interesting latest results of our own. Since this is the school, I'm mainly talking about the old stuff, just educational things, but at the end I would spend like half of the lecture showing you something new that is different from all what you can find in the literature, and it's just recent. And one of that is how to direct entangled states in the network. But today we'll concentrate on the traditional meaning of quantum communication. It's like secure transmission of information in the quantum cryptography. Well, I'll talk about first implementations in academia and in industry, what has been done. What you can see today everywhere around in the literature, in the professional literature, in the semi-professional and non-professional literature. There is lots of efforts talking about the quantum secure communication. I would like just to give you an idea of what it is in a nutshell, because lots of people who are talking about this today, very often they're just not very well aware of the real things. Because it just sounds cool to say, okay, we have a quantum secure communication. So it doesn't mean that it's really kind of what they want to do. And then we'll just talk about the perspectives of the whole area here. We started talking about this yesterday at the public lecture, basically, and maybe just conclude with that. Again, quantum cryptography. Well, you need to have security. Security of communication between Alice and Bob. And as always, there is a third person in the middle with the name Eve. She would like to take this information. So, conventional communication, as you know, everywhere goes using classical states. And Eve can always make a copy of that because it's a classical state. You can make a copy. That copy has to be decrypted. So the Alice and Bob, they use some kind of cryptographic encryption to make the job of Eve of decrypting this hardware. And that's a game that is going on in communications for tens of years, almost 100 years. Well, it was even in the past, older than that, but in terms of the modern communications, radio-related communications, that's what it is. The Alice and Bob try to invent new type of coding that Alice will have a hard time to decode, but Alice has no problem to get a copy of that. And basically the arrival of the quantum changes the paradigm here. Now the kind of emphasis is moved from the how hard to decrypt something that you can easily make a copy of into the, it's impossible to make a copy of, then you don't have anything to decrypt, basically. So that's a difference in the approaches to quantum cryptography and conventional cryptography. And as we already, I mentioned to you yesterday, so the Vernon cipher is the one-time pad, and the beauty of this cipher is that it's absolutely unbreakable if you use it only once. It has been used forever, and I mentioned to you about these radio stations that talk in numbers, because in principle, if you have the two sets of random numbers, you take the message, you digitize it in any possible way, and then you take every digit and you add random numbers to them. You know, the main rule of randomness is, it's very interesting. I learned this myself when I was a student. So basically, if you add random numbers to something, it becomes random. If you take random and subtract something from random, it's still random. You multiply random ones by something or divide it by something, it's still random. And randomness, it's, well, by the way, we discussed yesterday the issue of correlated, uncorrelated, the issue of correlation. So random, it means totally uncorrelated. If you try to measure correlation function of the random sequence, it will be flat everywhere. There is no any preferred relationship between anything. It's absolutely random. Okay, so if you do that, then you can send the message either way you want. You can use the radio, you can use like talk numbers, you can publish it in the newspaper, for example. People use that. So you publish a small, in the advertisement section, a small section with numbers in there. And nobody else except the person who has the second copy of that random set would be able to decipher that. That's it. It doesn't matter how you transmit it. It was very interesting when I came to US many years ago. I was still on Sunday reading real newspapers, not news on the computers, but the real newspapers. And that was a story in the Washington Post that people noticed this issue that people talking numbers on the radio, and they were saying that the closer you go to the southern border of the United States, the more frequently you hear that. It means the drug traffickers use that all the time. So it was very interesting at that time. Actually, I didn't do quantum cryptography yet at that time when I learned that. It was just a few years before. Yeah, you have a question?
Yes, like we add the same number for each character, or each character's key is different for one time?
Well, you basically, you at the end of the day, you can digitize it using binary codes and use binary random numbers. Just for each number, each like unit, there's like 0, 1, 0, 1, but it has to be in a random order. Or you can make another sequence of random numbers, not necessarily 0, 1. You can make any new sequence of random numbers, and then you can digitize your message, like using numbers, for example, number of letters in the alphabet, first, second, third, and blah, blah, blah. But then when you add the random number, it becomes random. Okay, so, again, the biggest problem of this is one time. And as I mentioned to you that, of course, the majority of people would like to use that because it's absolutely unbreakable. By the way, if you use one-time pad, you are not concerned about quantum computers at all. Because quantum computers is about the protocols like RSA that are based on the derivatives of prime numbers. So basically the idea is if you have a message and you can, if you can undo it and factorize it back and find what prime numbers have been used, then you can basically decode it all. And that's what the quantum computer is supposed to do. But it's not applicable here, so it's stable against any attack, any quantum computer attack. Yes?
Why can only use once?
Well, because then you introduce the correlation. Basically, you see, that's a trick. If second use,
It's easier to decrypt because...
exactly, because, you know, what is a correlation? It's some kind of relationship between what you are using, right? In physics, relationship, it could be like phase of 2 points, mutual phase or whatever. Here it's correspondence of the symbol to the particular letter. And if you step, because all the letters in the messages in language, they are correlated, basically. You know, like each language uses like more this letter, more that letter. There are big theory exists how to decipher it. And basically, using it second time gives you some hint which one is correlated to what, basically which letter is encoded in there. But if it's absolute, that's why the sequence should be really, really random, like 99.9% random. But the good news is if you have a sequence of numbers, there is a mathematical protocol that you can check the randomness, basically by correlation. And in fact, if it's not random enough, you can randomize it more, basically. Okay, because of this fact that it's absolutely secure when you use one, you have to refill it from time to time. In the past, again, there were books with printed numbers. Then I told you that those people start to put it on different carriers of information, like magnetic tapes, if still people remember that. Then floppy drives. Oh, they're flying so nicely, you know. Remember those 5-inch floppy drives? When I came over, I saw, oh, look, I bought like several boxes of them. 5 years later, I didn't know what to do with them, basically. I was just flying them. So then the floppy drives begin from 5-inch go to 3-inch. And then there were zip drives, then there were CDs, DVDs.
They fly better.
Huh?
CDs fly better.
Well, yeah. Actually, it's a good point. I still have a stack of CDs on the shelf in my office. You know, read-write CDs. At that time, they were cool. You can read and write. They were made multiple times on them, but I'm no use anymore. So, and then Blu-ray DVDs, and this technology was improving because originally you really, and military people, for example, they used that, and to refill the key, they have boxes of those CDs, and the military guards will transport it once in a month, maybe a week, whatever, between different installations, and then they use them. Just stick in the computer, use the program to communicate, throw away, and then next. And then you still have to refill it. And, but I mentioned to you also that the technology is not staying idle. Also, they develop in better storage tools, and the 10 terabyte drive can hold a lot of keys today. Which means that the motivation is getting less and less, really, to refresh the key, but still there, because it's flexible. Like, what if you your disk got compromised, for example, or broken, or whatever, then you need to have a fresh one anyway. So the quantum computer is supposed to cover that. All right, so basically you have to refill this from point A to point B, and that's really what the quantum cryptography is about. It's about the refreshing the random key, period. It's as simple as that. That's all the quantum communication is about. Refresh the random key, and then use a one-time pad after that. That's all. How to basically refresh the random key, that's what we'll be talking about. Well, quickly, so this is just a regular process of encryption, and as I told you, this is symmetric key So the regular internet encryption classical that we're using, it's non-symmetric. So there is the public key, private key, and other things. So this one is symmetric, both sides using the same key, and you just encrypt it, transmit, decrypt it, and that's what it is. But you need to have this key. That's basically what's, it all boils down to the fact that in the classical eavesdropping, if makes a copy or clone. Clone is a copy, right? So that's what it is, information carrier, and there is information from the copy. So basically, passive monitoring of classical information is possible. Well, you put a bug somewhere on the fiber line or electric line, and you read the signal all the time. In fact, actually, it's another interesting issue that you have to be aware of quantum cryptography. Quantum cryptography always protects only communication line from Alice to Bob. It doesn't protect the computers that the final and initial information is stored on. And you know that these days the electromagnetic surveillance is pretty powerful. Some of the people, they can read the keystrokes on the computer keyboard from like next room, for example, using the electromagnetic signals. Or sometimes even what computer signals from inside the computer box. So you do the quantum cryptography between Alice and Bob absolutely secure, you store that, and someone from next room just steals it. So that makes it not very useful. Anyway, have to remember about that. The quantum is different in the fact that Eve cannot clone the information, and she doesn't know the state of the carrier of information. That's the biggest distinction of classical versus quantum, and that's what really makes the original idea so interesting and attractive for practical purposes, to use non-clonability of quantum states, preventing Eve from making exact copy and keeping this copy for the future in order to decipher the message. Well, it's all based on no cloning theorem. There is a formal description of that by Woodard, Zurich, and Dix. So basically, you cannot make a copy of an unknown quantum state. So that's one of the rules of quantum mechanics, and we'll talk about this on the next slide. So as a result, it makes quantum cryptography secure. By the way, it makes superluminal communication by using entangled states is impossible. So basically, remember, superluminal not possible, and it's actually one of the consequences of this theorem. Well, the last one, quantum teleportation, seems to be also impossible. That's an interesting conclusion. I'm not going to talk about this more, but if you're interested, get curious, you can learn more about these things. What the quantum teleportation is about and how it relates to the no-cloning theorem, and why the modern quantum teleportation results are really not real quantum teleportation. It's teleportation only 25% of the information. Okay? But even if you do the better than 25%, if you go try to use the maximum theoretically possible teleportation, you will arrive at the limit of so-called quantum cloning, which is 75%. So basically the no-cloning theorem does not allow you, people call it quantum cloning, because it's a cloning with fidelity of 75%. So the question is, like, if 75% is right here, then do you want to be teleported down to the top? So that's a very interesting question. Anyway, so what is no cloning? There are lots of different definitions of that and derivations of that, but the most simple one, basically, if you have two states, A and B, So basically, and you act on them with the operator U, then if it's a regular kind of unitary operator, then the final state time final states would be product of initial states. If by any chance your operator is such that it creates two states instead of one, let's imagine we go from the opposite. Let's say copying is possible. So basically the action of this state is instead of one, make it two. One and second is a clone of that. So then when you multiply them, you will have it will be BA squared. So this one and this one, but in quantum mechanics it's the same state. So this should be equals to that. And then that's really like you ask yourself when this is possible, and this is possible only when they are either equal to each other or they're zero. So that's basically what the proof. It's mathematical. I'll tell you the physical explanation, my personal physical understanding of no-cloning theorem in a minute. So, and superposition principle, so also with states, horizontal vertical states of photons, it's also the same thing. If you have H goes to HH, V goes to VV, then if you have H plus V, it has to go to this, but it's not like this times that. So it's not a two final states, it's different. So you cannot make this out of that. That's another way of explaining this. Well, now we're coming to polarization, photons, and mutually unbiased basis. Mutually unbiased basis is 0, 90, and 45 on 35, basically. So orthogonal and diagonal. Why they are mutually unbiased? Because every vector from one state, if you try to project it on the other one, it will give you superposition, but it will be equal superposition. So basically, 90 to 45 will give you plus minus square root of 2, basically. And vice versa. So basically, they're equal projections on the other one. That's why they call them mutually unbiased. Why this is important here? Because polarization works by projection. So if you have polarization state and you would like to measure it, how you measure polarization? You take polarization analyzer, and you project your state on the state of the analyzer. And what the analyzer does, it either allows you to go through or not. If the state of analyzer coincides with the state of your photon, it's 100% pass. When it's like 50% like this, then it's a 50% pass, right? So what does it mean, pass? Pass, it means you can put your detector and detect this event. So, and then, based on this detection, you make a conclusion of what was coming. So if you have a vertical photon coming and your polarizer is vertical and you have a detector, so 100% pass, 100% every detection you have tells you the truth, that it was a photon at this orientation, right? But if my photon comes at 45 degrees, I still use the same analyzer and detector, then 50% of time I will have some clicks, but it will be wrong. Because this 50% of time, the 45 degrees can generate clicks 50% of time. But the conclusion, I would think that it was vertical, but in reality it was 45. So that's a source of error when you do that, using mutually unbiased basis. Now, physical explanation of no cloning, like how you could resolve that this thing. So basically, if you take and go to the level of single photons, and if you encode your polarization state in these two bases, but on every single photon, remember, to detect the photon is actually one of the major problems, feature and the problem of photonic quantum optics. You want to get information about the photon, you have to kill it. You absorb it, you kill it. There is no second one, basically. With the particle, if the particle has a spin, you measure the spin, You disturb your particle, but it's still there and it still has a spin. Disturbed, but spin is there. You can reuse it for some purpose. With photons, it's gone. So that's really the physical essence here. So you have single photon and you encode it either in one basis or in the other basis. So it's a twofold ambiguity. There's one and another. So two options you can have for one single photon. But when you detect the photon, you kill it. So there is not enough energy to resolve the twofold ambiguity with one quantum of energy. So that's a physical kind of description of why quantum cryptography is secure and why you cannot flow. If you would have two photons, then you can do that. You do two measurements. And then you can conclude was it true or not, because you can do two measurements. You can make first measurement in this base, second measurement in that base, and see which one is happening more frequently. So that one will be a real state of the photon that is coming in, so you can identify it. But with one photon and one single measurement, you always will have 50% chance of error. That's basically the bottom line. And also it's why all, I will talk about this, all practical implementations of quantum cryptography always require a very nice, clean single photon state. The minute, instead of single photons, you will have double photons in the pulse, you are vulnerable to the resolution of this paradox, and then your cryptography will be not secure anymore. Okay, so that's the role of photons and polarizations. So basically, the protocol is very simple. Well, first, let's talk about the single photon quantum cryptography. Bennett-Brassard 84, quantum key distribution, classical encryption, uses basically is based on distribute random key and then do the one-time pad. Basically, that's what it says here. So quantum key distribution and then one-time pad, that's what the secure communication is about. Now we have to establish the key. What the procedure? The procedure is, the first thing, we set up the base. So vertical is 90 degrees, and 135 will be 1, and 045 will be 0. And then Alice sends photons, and what she randomly switches the base in which it sends photons, but also in addition to changing the base, she selects one of the polarizations. So remember, there are two things: base and which particular polarization in this base has been used. Two types of informations, and they are randomly modulated. So you randomly select which base you use and randomly select which polarization inside that base you use. And then you use this map to say, okay, that's what basically Alice is trying to say, send in terms of the logical bits. They are encoded in these polarizations. Now, what Bob is doing, Bob is coming with the analyzer, polarization analyzer, and has two choices. You put it this way or that way, and then detector behind to measure what came through. So that's what Bob does, and that's what Bob detects. Okay, but Bob again randomly chooses the measurement base. So you can already see, so 50% of time, Bob will pick up the wrong base because it's random, right? So, and what is red here is when Alice selected one base, but Bob selected the other one. Well, how to deal with that? What Alice and Bob do, they take the public communication line and reveal the bases. Revealing bases doesn't reveal the whole information because you do not reveal which state inside the base you use. You just reveal which bases you are using. And Bob compares with what he was using, and obviously 50% time it's wrong, so he just drops those. So immediately you have 50% overhead on the communication. So 50% of your information immediately goes to waste. After that, After that, they know that they did the measurements in the same basis. Okay, and now they have to figure out whether there was any problem in communication. Are there any errors in communication? How you do that? What you do, you take these recorded strings and you subselect randomly small portion of that. I don't know, maybe like 5–10%, but randomly through whole sequence. And you reveal it. Again, through the public channel, Alice and Bob compare what, like on this bit, this. They check results for some of the cases, as again, randomly select. Of course, it's now waste because they publicly announced that, but it's not so large percentage, but it allows them to evaluate how many errors they encountered. So if they all coincide, perfect, it's 100%, no errors, but it's very rare. Actually, it never happens. So then, let's say you have errors. How many? What is the percentage of errors? And that's an interesting issue because, well, the communication line is long, it can disturb the photon parameters, polarization and everything. By itself, it will introduce errors. But then there is the problem of the eavesdropper. I will talk in a minute about. So after they communicate this, and now they have finally the secret key known to Alice Bob, and they know with what error this key is obtained. So that's the first stage of the evaluation. Well, again, so there are two. Let's see. I'll come back to this in a minute. So if when it comes to the line, we'll do exactly the same what Bob is doing, right? Because it's a single photons going through the line. Your job is to pick up the single photon, try to guess correctly the state of this photon, make a copy of this clone, and send it back to Bob, right? Then, if everything works well, then Bob will still do what he has to do, but you have a copy of that. And when it comes to the end, you will have a copy of the information, because you can monitor all the public information between Alice and Bob, and then you have everything for the future use. So Eve does the same, takes this measure, but again, the same as Bob, Eve will make 50% error in evaluating what polarization is. But then this error will go propagate towards Bob, because the copy will be made and sent to the Bob. And then Bob will do his own and takes another 50% error on what it will send there. So it's like 0.5 times 0.5 becomes 0.25. That's where this 25% margin of security comes about, basically. So as I said, so the Eve can get up to 3/4, 75%, but 25% will still be the error. And this is really the indicator for the legitimate users that someone is listening on the line. How you reveal it? Exactly from this stage that we just discussed right here. If you start doing you start comparing those results, and suddenly you find that you have more than 25% errors by randomly checking the things, it's an indicator someone is listening on the line. What you can do? Just drop the line. That's what it is. Go to another one, check that one. If that one will come not with 25, but for example with 10% or 11% or 5% error, which means, okay, that's no eavesdropper, but there is some noisy propagation and whatever in communication. So, basically, if I have, for example, 10% error, it's a substantial error, right? So you don't want to use this for encoding, because no one was listening, but the Alice's and Bob's strings have 10% errors between them. you would like to have as close to 100% as possible, because then it becomes clean communication. So what do you do with this? In principle, you can improve the quality of this to make them equal, those strains. So it's called the privacy amplification protocol. How you do that? Well, the best one is to test the parity. It's a very standard procedure everywhere, like even in randomization. So you have a string of numbers. What you do, you chop it in blocks, like let's say 8 bits, for example. And then you check the parity of this block. So because they are 0, 1, 0, 1, 0, 1, it's either even or ordered. You add them, you sum them up, and you come up with the number. If it's odd number, you say, okay, this block has odd number, next one even or whatever. So, and Alice and Bob do the same, and then they publicly compare are they same or different parities, because you don't reveal the information. You reveal only some of those things. And if, for example, your block, Alice's block and Bob's block have the same parity, you say, check, it's good. They are exactly the same. When parity is different, what do? Drop it. Same, keep. Drop. So at the end of after that, you lose part of the stream, but what remains has much higher degree of fidelity and lower error. So it's a standard process in nature. So you throw away something, but you boost performance of something else. Yes?
Yesterday you talked about entropy, not in physics, but in probability. I want to ask that, why don't we use polarization or filtering to get higher level of percentage in entropy and make the communication better?
No, but that's what we use. We use polarization here.
Yes, but we always get the 50-50 percentage.
Yeah.
Why can't we make it better, or
How you can make better? You need to prevent Eve from getting information. The best way to prevent from getting information, make equal probability of having right and wrong. That's what the principle. If you change this ratio from 50-50 to 70-30, you will have biased situation. So Eve can gain more information.
but isn't it a better way to make a good communication?
What do you mean? What's the better way? The better way, we're not making communication, we're making security. Security means lack of information obtained by the third party. The lack of information, the best way to have a lack of information obtained by the other party, to make things random. Right?
Yes.
So randomness is the limit. You can express it in
It's better
entropy
to
values.
use 50-50% always, right?
Yeah,
Okay.
and that means you have zero information.
Yes.
And that's a purpose. Security. I know you would not know, because you have 50% chance of making error. That's the principle of secure communication, using quantum. Okay, I saw there was another question. Okay. All right, so basically you can increase the fidelity and decrease the rate, but basically you trade the quantity for the quality. So at the end of the day, the other interesting thing is everyone would need to do that, because, well, there is some agreement at which level you can use secure communication. So you have to bring it like to 99%, for example, which means you have to do this procedure of privacy amplification using parity, so lose something. So if you go back and ask yourself, oh, how much I have to lose out of those bits to get to 99%, so then you, because you start from some error. like from 10% error or from 15% error. The more error you start with, the more you have to do this procedure and the more you lose the real key rate numbers. So basically, like out of everything, there are some theories, estimates, basically. The idea is your communication line should not introduce more than like 7–10% of errors. If you have just Alice Bob do this and they come up with like 15% of errors, to get it back to 99%, you will not have enough keys to process it, because you will keep improving, and your line of keys shrinking, and you don't have enough room. So basically, you really have to clean up your communication line, make sure, we already know, because it's less than 25%, there is no eavesdropper. All the errors is due to the quality of the communication line. And communication, if we're talking about polarization, for example, you take polarization photons, send it through the fiber. I don't know how many of you have experience with that, but you know this. What comes out on the other side of the fiber can be pretty much not exactly the same polarization. There are lots of efforts needs to be put into the stabilization. Okay, yeah, that's what I told you yesterday. So about the, how to do this with, you just encode it like single photons in horizontal and vertical, or 45 minus 45, and that's what it is, and AIF does the same and gets 5% effect. Okay, very well, now there was the single photon communication. So you take a single photon source, send it through the modulator to the Bob. Bob demodulates, EIF also sometimes demodulates, and it's a single photon. The single photon and double encoding in mutually unbiased basis tells you, gives you a reason to reveal the eavesdropper, and that's what kind of shows you the quantum nature of security. It's in the single photon and double ambiguity in the mutually unbiased basis. Okay, there's another approach to quantum cryptography. It's based on entangled states, Eckert 91 protocol. So it's based on the source of entangled states. One photon goes here, one goes there. If you create this entangled state and do the Bell's inequality measurement, we discussed this yesterday. So you have, as you remember, what we have violations of Bell's inequality in these areas around the 22.5 and 67.5. Sorry, this one, yeah, 67.5 angles. So this is the quantum margin. This is classical. So basically, it's based on the fact that if I send these two photons to one side and the other side, if I do the Bell's inequality test, if no one is on the line doing anything to my photons, well, except that the communication line is going to spoil them a little bit. And I told you that in quantum mechanics it's very important, the properties of the source, properties of propagation, and properties of detection, quality of that, for the final result of the measurement. So if everything is fine, I will see this. Okay? Now, if the eavesdropper will come in the line, in either one side or another, and we'll try to do the same thing, then make a copy and resend it back, this will be limited by the classical domain only. Because measuring, as I told you, measuring the quantum state will bring you into the classical domain. Then you make a copy of that, you send it back, and basically you already operate only in the classical domain after that. So you'll not be able to do the violation of Bell's inequality. So it's a different physical reason to break the quantumness of the state. It's based on the fact that you create this state, but you cannot clone this state. No cloning means you cannot make a classical copy and then reintroduce it and do the same measurement again and get the quantum result from the whole thing. So you basically break the if appears either here or there, it breaks the quantumness of the system. So you are in the classical domain after that. So if you, after that, it will be purely classical, so you cannot demonstrate violation of Bell's inequality. And again, here it's, this is the margin of the eavesdropper detection. And if you look carefully, it's about the same 25%. Similar to the previous one. So if you do everything and how you detect it, you do the same thing. You do the detection at different angles. You can select even the same parameters. Well, except that to stay at the maximal violation of Bell's inequality, instead of 45 minus 45, you have to use 22.5 and 67.5 degrees. And that's how you do it. It's called the ACAT protocol. And the result is the same. While the quantumness the quantumness of the state ensures that whenever you do something classical to this state, your result will be distinguishable within 25% from what quantum mechanics predicts. In both cases. Well, to some extent, you can really draw the analogy between these two. So, because it looks like the purpose is the same, and the tools are quantum photonics, right? It should be similar. What the similarity is about. Okay, in principle, what we can do, we can take this entangled source and move it here to Alice, basically, and then it becomes almost the same apparatus as before. And then you can ask yourself, okay, there are two types of technology. The first one is based on the entanglement. Remember what the entanglement is about?
Correlation and superposition.
Correlation and superposition. Okay? What is the two bases that mutual unbiased, the two polarization with mutual unbiased bases? They give you superposition, right? One projection of one on the other one is a superposition of two. So superposition is there. We need correlation. So when you use entangled sources, the correlation and superposition is already embedded in the source. In TBAE84, you start with single photon, so you do superposition. Where is the correlation? Remember the portion of the communication when you publicly tell what base you are using. So this is the analog of correlation between outcomes. It's kind of like semi-classical correlation, but you can draw the analogy between these two technologies based on that. Well, the entangled source is kind of slightly harder to operate than just a single photon source and modulator, because single photon source is just laser, you attenuate it, and that's just attenuated laser. You just have to attenuate it enough so per each pulse of the laser, remember you need to have one photon. But laser itself, it's a coherent state. Coherent state statistics is Poisson. So you have a pulse and you have a Poisson. Poisson, if you remember, it has a probability of having 0 photons, 1 photon, 2, 3, and so on. In our case, we want to have 1, but we don't want to have 2. Well, when you have a Poisson, no way you can avoid this. The only thing you can do, you can minimize the amount of 2 versus the amount of 1. How you do that? You have to make sure that average number of photons per pulse is substantially smaller than 1. And lots of calculations and theories tells you like around 0.2 photons per pulse. That's where the number of single photons is like 9-10 times bigger than the amount of double photons. So you have to watch for the intensity. Yeah.
I want to ask that. I think I missed something. You add the second source here.
No, it's like if this one moved in there. No, it's like you move it right here. So when this one here, this one is not. So it's just you see, it's indistinguishable from a single photon source. So qubit is coded in the A basis and holds the bit value given the Alice's result. So you basically either can have source in the middle, or you can move the source to the Alice's side. Yeah, it's basically the same. The one interesting thing here is, remember the quantum mechanics is the linear theory. Linearity is a powerful tool. Basically, whether it's here or here, from the linear theory, it's the same thing. Yeah, sure. Yeah. All right, so, yeah, okay. So, the quantum cryptography has been done many times in many different areas. So, for example, here it's between two mountains in Alps, using polarization encoding in free space over 23 kilometers. Actually, the free space happens to be better for polarization encoding than fiber even. It holds polarization better. You need to encode in different polarization bases. The first experiments were done with like basically one laser and then polarizer, a Optical cell basically that rotates polarization. But Optical cells, it's a nonlinear crystal, basically a piezoelectric crystal that you have to apply like 1.5 kilovolts to change the polarization and so on. And it's only a particular frequency you can reach with that, because switching 1.5 kilovolts with nanosecond time, again, generates lots of currents. You cannot do that. Like 30 kilohertz was the maximum rate you can start with. It was not good, you need more. So what people did, they say, okay, let's take the different approach. We have 4 lasers, same intensity, but we put different 4 polarizers, and we merge them in a passive way on beam splitters. So now, if each laser operates at pretty low intensity, then overall intensity is still low, but you don't know from which laser the next photon is coming. So it's a random encoding in 4 polarization states. It goes here, and then this is the detector. The detector is again passive. Passive analysis. So here it's a non-polarizing beam splitter divided in 2, but then this is polarizing beam splitter, one polarization. So basically this would be like 0, 90, this one 45 minus 45. Well, the only thing here, it's stable because there's no active elements, it's passive, but you lose 50% here, because if you are polarizing 45, but you go in this direction, then it's a wrong thing, so it will give you the error. So 50% gives you errors, but then you buy the very stable apparatus that doesn't require any modulation, and the rate is only defined by how the lasers and how fast your detector can resolve the photons. Remember, the quantum state has to be created in such a way that it will be one quantum state at a time. Then propagation should not distort the states to mix the neighbors. And then your detector should be fast enough, again, to distinguish each separate state arriving to these detectors. If your detectors are too slow, you have to reduce the flux, because then you will have pile-up of pulses on the detector. Two states will be coming to the detector, and it will not be able to distinguish that. It's average. It's already a semi-classical state. Phase encoding. Well, phase is the same thing. You can instead of polarization, there is a big analogy between polarization and just regular dynamic phase. So basically polarization has 360 degrees, and regular dynamic phase has 360 degrees. You can do the same thing. This is like a big interferometer, but there are two arms here. It's not good. So between Alice and Bob, you need two lines. So how about do something like this? We have one interferometer here, one line, one interferometer here. And that's a very interesting situation because in principle, when you start detecting this, there are four options. Because it looks like you take a single photon pulse, you send it here, and it can go either through the long or through the short path. And here it can also be a combination of long-short. And if you ask yourself, there are four combinations. The same, like remember, the beam splitter gives you four combinations as well. So your detector will detect, this is short-short, long-long, but this one will be short-long or long-short, and they will be the same. Okay? And that's where the interference comes, because interference needs superposition and indistinguishability. Only these two are indistinguishable. These are distinguishable. So what to do? If you detect them all, you have classical situation, four options, like we discussed, so it's not entangled. But if you put a window here and only detect events within this window and just ignore those, remember the operational entanglement. So you filter out something and it looks like entanglement. So the same thing is here. So if you don't detect, and this is what it's your detection apparatus. It's up to you to register this or not to register it, or only concentrate on this central peak, and that's how it works basically. The only potential problem is you need to stabilize the path difference. So this interferometer should be exactly the same as this within very high accuracy, but it has big advantage. What is the advantage of this? To have good interference, you need to have long coherence length. Long coherence length means the narrow spectral bandwidth. And narrow spectral bandwidth is very good for fiber communications. Because when the bandwidth is narrow, there's no dispersion. Remember, dispersion is different speed of different frequencies. And when all frequencies are the same, they all have the same frequency. So that's really, was one of our discoveries when we tried to do practical QKD in telecommunication fibers. And then there was another interesting development, and thanks to our Nicolas Juzin at the University of Geneva, they came up with very, very interesting solution of the problem like if you go from Alice to Bob over a lengthy fiber, you pick up lots of different modulations. Fibers can be either twisted a little bit, or it could be different temperature, different tensions, and so on. All of this will give you phase changes of the light going through. Yes?
Can we use polarization and phase same time?
They are indistinguishable. It's a separate topic, but they're basically indistinguishable in terms of their effect. You can, but you cannot distinguish that. When you don't, it gives you extra problem and ambiguity. So, this one is basically they call it plug and play configuration. What does it mean? You need to have single photon goes from Alice to Bob and encode it there. What they did, it was very smart. They start with Alice and they send through the interferometer, but very strong pulse, not single photon, strong pulse. Strong pulse of light to the Bob. But while going through the fiber, the strong pulse of light picks up all the modulations on the way. But then Bob attenuates this to the single photon level and modulates and sends back. So when you attenuate all of them, because each photon basically in this package of intense package has the same information, carries the same information about phase modulations, disturbances on the fiber, they send it back but sent back from the phase conjugate mirror. Basically, you just reverse the phase and send it back, and what happens is you automatically undo all the phase modulation. So when it comes to Alice, Alice does the job of original Bob, and the protocol works the same, but now because of this double pass, first intense pulse and then real weak pulse, because when you send intense pulse, you do not affect the distance. The distance is defined by the single photon, how long the single photon can go through, and really it improves the stability, quality, and everything, because this pulse compensates for all the imperfectness of the communication line. And it was so good that they can take it any fiber you want, connect it, and just this self-correction of the parameters of the fiber made it really plug-and-play option. By the way, just pay attention to the dates on all those results and compare with what you hear today about things. All right, this is what I've shown you in Boston when we did this DARPA quantum network in early 2000s. Exactly, we selected first fibers and we did the phase modulation, but in principle we had two options. Basically, this was the phase modulated line with weak coherent, but then we had the entangled, but we did this with free space because free space is better suited for the polarization. People did the polarization encoded in fibers, but they have to lay down specialty fibers. They call the polarization preserving fibers. Because if you have a regular fiber, circular single mode fiber, you send polarization and it will just go around, because whenever fiber bends, you will create internal birefringence and it will immediately turn your polarization. And or your fiber goes and then there's some kind of train or heavy truck goes by the road. You know, they usually put fibers either along the rail tracks or along the roads. And that affects the quality of the communication. So it's basically, here it's straightforward: source, modulation, channel, demodulation, and detectors. Here is source on linear crystal. One photon stays with Alice, and second one goes to the Bob. Although it's called the Alex and Barb because there were several channels. Alex Bob was the main channel. This is the second channel, A and B. The idea is, well, then when you do that, the distance, you know, single photons are photons. They get an absorption is universal property. It's always there. And you can create so many quantum states in the beginning. And then you start propagate them in the fiber or in the free space. You always have to know how much will reach the detector. The closer you come, the more of them. The farther away, the less. We discussed it yesterday. So you move it 500 kilometers, you get almost nothing there. So, but even in the communication, when you do this inside the city, in metropolitan network over like 10, 20, 30 kilometers, you do it, well, we can have maybe 50, maybe 100 kilohertz, 50,000 or 100,000 events per second. And if you compare that with the traditional internet speed, then it's way, way, way below, right? So the question is how to combine the speed of the regular internet communication. This is the IPsec, one of the protocols, security protocols on the internet. And with the physical layer right here, this is our physical layer. So we run this physical layer right here. We get bits. Then we put them, you see, like we deposit them in these buckets. And this machinery of quantum key distribution does all the sifting, cleaning, distillation, and privacy amplification. So a really, really nice, clean sequence of bits deposited here, and it's available for the telecommunication encoding, but the rate of arrival of these bits is multiple orders of magnitude lower than there. So the question is how to deal with that, how we can, at that time where it was really serious, how to sell this to industry basically. And what we tried to do, we said, okay, if you do the regular browsing on the internet here, maybe you don't need such a high security. But when you try to make a payment for something, you would really like to have high level of security, then maybe to encode your credit card number and the security code, you would like to use the most secure kind of block of communication, very well protected. Not regular key, but the quantum key for securing this one. Then it becomes more or less doable and useful, because the amount of bits to encode this really sensitive information that you'd like to protect is not so large in this situation. Again, it's for the kind of general internet use of secure communication. Of course, military people, they say, we all secure, whatever we say should be secure, and even their boring meetings are also secure. So they want to gigabit of secure keys. It's just what do we need to match the entangled-photon links with the real telecommunication equipment. It's just a kind of block diagram showing you when you go deeper and deeper in technology, things are really getting involved in there. Well, as I said, at that time, of course, since technology was developing, there were startups. People tried to make business out of that, right? So to make secure solution. And there were a few of them. One of them was Magic U Technology in Boston. They asked me to set up their labs in Boston. And this is the boxes, basically, that you can connect. One goes to Alice, one goes to Bob, and you can do this secure communications. This is the ID Quantique, also one of the earlier players in this business. They use their boxes. This is Alice. Bob used their plug-and-play system that was working nice. This all information is about, let me see what else. I think there are some Japanese systems also for this. That's the interesting thing is, it's just 20 years old. And now you hear we have quantum cryptography, quantum communication start up here, quantum there, everywhere. And is it good or bad? It's very interesting. First question. If quantum cryptography is so great, why those first guys didn't make $1 billion business on that? If you ask yourself what they're doing right now, actually there are this ID Quantique and Magic Q, it's few of those that survive, that's still alive. But they're basically doing something else now. They still can sell those boxes, but only like 1, 2, 3 per year, that's it. It's not a business. Market is low. And if you try to do the business about this, you have to know how to do business. So at that time, we tried to set up a startup on different type of things, but we learned lessons how to do that. So if you go to raise money from the venture capitalists for your company, do you know what first question they ask you?
What's the speed?
No.
What is the profit?
Well, relative. So what is the market? The market size. They're not really, then second question would be, what kind of team do you have for your company? And only third question would be what technology you're using for that. Okay? Market, because that's the size of how much you can sell. That's how profitable your company will be in the future. That's the reason why everywhere in the world people are trying to erase trade borders, right? All the trade agreements between countries, like European Union, North American trade agreement with Canada and Mexico and all others, whenever you hear about them, it's an attempt to make sure that the company inside each country can sell to everyone without constraints, as much as possible, the market. Well, how about quantum security? Why it's not selling to, why those companies making those nice boxes, they couldn't sell to everyone? At some point, which has also been a long time ago, so I was helping the Italians to build up their own first quantum cryptography system. And that's where it occurred to me, this, where I realized this. And I realized it on a small event. We have a project for about already 3 years. We had some system to demo. And then military people from Italian government who gave money for that, they were the same as the US or DARPA was given, but we were doing public kind of research on that. So they came in and they asked me to leave the room. Because, yeah, I built it up, all the things. Okay, we'll be discussing it, but you have to go. You're a foreigner in Italy. So that's how I realized that the cryptography, security solutions, is a completely different type of commodities than anything else in this world. It has natural borders, trade borders. No one would buy a security solution from across the border. So basically, if you want to make a business on security, well, be careful, because you have to figure out how many of the systems you will be able to sell. So that's an I hope all these dozens of new startups that I have seen in Munich 3 weeks ago. It was a laser show and the Clio Europe laser conference with lots of quantum everywhere. So hopefully they will realize it sometime. But at the moment, well, they're raising money. They go and burning through this money. They're learning. They're educating students. There are lots of postdocs going from instead of academia into the companies and so on. It's a good process, but at the end you have to know what will be at the end. So you have to do the educated conclusions or educated prediction for that thing. Okay, so again, this is the distance. This is secret bit rate per pulse, or per pulse, or whatever, per second. You can do it per pulse or per second, it doesn't matter. It's a rate of secure bits, and this is the distance. And basically, it's detector noise limits. Then this is the optical noise. This is the limitation if you cannot do the single photon when multi-photons per pulse start to come, or the Eve comes in. So that's where the limitations in the distance of secure communications. If there is no Eve and there is no multi-photon pulses, then you can go to here. And then if you reduce optical noise in the system, you can go there. If you reduce detector noise, you can really move it maybe right there. And that's exactly what happens today, and people trying to push this as much as possible. I told you to like 500 kilometers, but the rate is somewhere right here. Like if this is 10 to the minus 6, it's really like right there. So your 10 to the minus 6, it's per pulse. If you do 1,000,000 shots per second, 1 megahertz, then it will be 1 per second, basically. Then it will be 1. But then I told you it's 0.01 per second, it will be like right here. So people reduce optical noise, reduce detector noise, and reach that point. But again, the question is how much is much in terms of the coverage. And the only way to increase the coverage, as I mentioned yesterday, is to link your regular communication fiber network with the satellites And basically you do the kind of, Alice sends this to the satellite, and then satellite drops it to Bob, to another Bob, whatever. So covering at different places. Well, as I told you, it's good, everything is good, the distances can be covered, but the weather conditions are important. Should we kind of keep fibers? Well, that's a good question. I've shown you this Chinese communication using satellites, but by the way, Chinese have also the communication line from the Beijing to Shanghai in 32 nodes. Basically, remember, this is quantum, no repeaters, no amplifiers. So it's from point to point, point to point. But at each point, at every computer, you have to have a military guard staying there. And that's what they do. They have lots of people there, so they have secure communication in fibers from Beijing to Shanghai with like 32 nodes and 32 computers guarded. So to make sure that security is good.
Why they don't load 10 terabyte hard drives?
Huh?
Why they don't load 10 terabyte hard drives, as you said, between
Well,
those
you can tell them that. Anyways, and see what happens. Anyway, just to tell you that, and of course all this happens after 2013 when Chinese decided to launch their satellite and put billions of dollars in that. There's very lots of, so if Chinese is doing this, we also have to do that. You know, like, lots of money is flying in this area, and some people are successful in grabbing this money and using this. But just to tell you that this issue has been, the balance and all the pros and cons have been investigated by my colleagues at Los Alamos, well, back in 2002. Those colleagues are long retired now. So, but they knew everything about that. It's just an example, but there was like public lectures. They've shown the balance of the balance sheet of all the kind of how frequently you can send, kind of receive. But the problem is the satellites are moving. So first you have to find, just catch the satellite shows up, establish the link. It takes some time, right? Regular kind of arranging to the satellites to find, okay, lock it. And then get the exchange of the data, and then that's it. The whole thing is about like 20 minutes. So you use a few minutes in the beginning, you use a few minutes at the end, on the sunny day, on the clean day. If you have a cloud, forget it, it's gone, basically. So lots of interesting details if you go inside there. At the superficial level, it sounds great. That's exactly what you hear today everywhere in the news. But when you start to dig into the real technology implementation, you have to fight Mother Nature that is classical. It doesn't like quantum very much. And it's a general rule for quantum. It always works somewhere. You have to find some niche where it can work, because you have to avoid the impact of our classical world on the quantum environment and destroying this environment. And the clouds is one of them, basically. Because if you have, well, actually the clouds are so bad even for classical lasers. You know, all these programs of the powerful lasers on the, either on the ground or on the airplane to shoot missiles. They've been around for 20 years now, and have you seen any successes? You've heard that there are successes, basically. But the problem is how to deliver high power to the point in the atmosphere, where atmosphere is classical environment of turbulence, clouds, and everything. It's a big, interesting problem if you start to look into details of that. The same is here, except that we don't have megawatts of lasers. We really have single photons going inside there. All right, so, and again, if you want to learn about basics of quantum cryptography from the first way for people who did that, you can check this book, and thank you for your attention.